Thanks for having me. Thanks for the very warm welcome. I'm Daniel. As said, I'm a PhD student and research associate in Cambridge. And I work mostly on anonymity networks. And I think this particular project is also interesting for the audience in the room, because we're going to talk about multicast. And we're going to go through the title in a bit more detail in a few slides, so we can unpack it together, because it has lots of words in it. But why should you care? Well, if you have more than one peer, if your n is bigger than 1 or 2, then you probably use some multicast somewhere in your systems. So ideally, you should care about it. What we're going to do is we're going to walk through first the problem statement, talk about what we're actually trying to solve. Then I present Rollercoaster as a very simple idea, how we could solve that problem. Then we figure out, oh, it is not that simple after all. So we have to build on and tack on some more optimizations to it. In the end, we're going to look whether it's doing well after all. So the problem. From the title, there are at least 3 things that might be of interest to clarify. There is like mixed networks. I assume most of you have not heard about mixed networks. There is Group-Multicast, which probably makes sense to some degree, and there's efficiency, which is always very subjective how we specify that. So, mixed networks. So the very brief summary is that mixed networks are a form of anonymity networks. The idea is your messages that you want to send out go through multiple hops where they can get delayed, mixed with other messages. Similar to Tor, they have layered encryption, but different to Tor, they all travel independently, so there's more mixing, more quote-unquote anonymity happening, so they give you some stronger guarantees. So that's pretty nice. And it's a very decentralized system. It gives you quite low latencies in its latest iteration, so think about a few seconds maximum. But there's also no implementations like NIM, which goes sub-second, so you can even do fast transactions over it. It's built with mobile clients in mind, so there are mailboxes when your smartphone, for instance, is offline. The provider node kind of caches the message, and then you can get them later on. And there's a concept that we call cover traffic. And cover traffic is a quite neat idea, so it hides whether there's any communication at all. And the way this works is that every client kind of has 2 queues. We have one queue that's always filled with made-up cover messages that go nowhere. And then if your application actually has to say something meaningful, they put a message in the payload queue. And then there's a timer, and let's say every 5 seconds, we send out a message. Then someone who looks at your internet connection can't tell whether you're doing any meaningful communication at all. That makes it very hard to correlate who's talking with whom. Then Group-Multicast. That hopefully doesn't come as much as a surprise. So for this, we assume we have a fixed known group of people. Let n be 8 for the rest of this talk. And anyone can send messages to anyone else in the group. For instance, we typically assume, okay, A wants to send a message to the group, and then afterwards, what we want to see, well, everyone got the message and got the content. And one example application that we are interested in are collaborative tools. So if you have something like Google Docs, you usually have a central server. Everyone sends their updates to that central server. The central server puts them in a certain order, generates a document state, and then everyone can query the server, oh, what's the document currently looking like? But you can, of course, do this also peer-to-peer. So you remove that central server, which gets all the data, which can tell who's talking to whom, and also along the way you improve availability, because you're no longer reliant on, for instance, Google keeping their service running. And all these updates, whenever you type a word, change your formatting, you kind of need to propagate that to everyone else who's on the document. So you have this many-to-many group multicast communication. And efficiency. So we are interested in the application level latency. So from when the sender does an action to when the recipient can see that action. And because we're talking about groups, we're actually talking about a latency distribution. We're quite interested, okay, what's the average? How long does it take in the worst case? All these things, we want to be as quick and as fast as possible. So first thing first, we're going to talk about some naive solutions that might be already floating in your head, and they don't work. The first one is unicast. So, okay, well, A could just send a message to B, send a message to C, send a message to D, and it goes on and on and on. And then in the end, well, everyone has the message, but this will take a long time. As long as we have members in the group, so we grow linearly with the group size. And what that will do with our payload queue is actually, oh yeah, that's going to start to overflow. I add a word, okay, 8 messages to the payload queue, so we need 40 seconds to clear. And if I, in that 40 seconds, do another action, well, just keeps on growing and growing and growing, and we really can't catch up. So this doesn't really work. The other naive idea would be, oh, well, we have all these machines in the middle, right? When we send our messages through the mixed network, well, can't they do the work for us? Can't they just forward it to everyone else? So something like this, we send this big message in, and then we pick a multiplication node. That node multiplies the message, and then it delivers to the others. Well, there are 2 big drawbacks here. Our messages have to become really, really big, and we don't want to make them different sizes when we send out messages, because then people would be able to tell, oh, you're sending a message to a large group, you're sending a message to a small group. And also the multiplication node would learn the size of a group. So we would be leaking information in this scenario, and that's something we don't want, because, I mean, we got the strong anonymity network, why break it for group communication? So let's talk about Rollercoaster. So the idea of Rollercoaster is actually pretty simple. So we do the first step as before, so A sends a message to B. And then the next timestamp, of course, B can help us. So B can send a message to C while we send something to D. And then you see where this is going. There are 4 people have the message. 4 people can forward the message to the next 4 people. And then everyone has it quite quickly. Hooray. And if you paid attention in your algorithm classes, then when the solution size doubles in size in every step, then we go from linear to logarithmic. So that actually makes this go pretty quick, which is nice. And also, we improve the global efficiency, because you must imagine like everyone in that group, because they're part of that mixed network, continuously sends those cover messages. And by helping us to distribute other messages, we improve the ratio of payload to cover messages. So the entire system gets more efficient. Cool. It's not that easy though, I'm afraid. So we have to look at a few things where we can make this work better. And one thing is fault tolerance. So what do we do if B is on somewhere on the beach in Greece and don't get a chance to really participate? So when we remember our distribution or like our structure from before, will kind of look like this. Oh, well, our messages to H and D and then E, they're all fine. But everything that went through B, well, that's not happening, because they're offline. They're not helping us. And then like C, G, and F going to sit around and wait. And they don't even have an idea they should be waiting for a message. So that's not great. So we kind of need some fault tolerance in our scheme. And the simple solution is that, okay, everyone who receives a message just sends us a little acknowledgement message. Says, oh, I got your latest message with that ID. Here's a green check mark, and all is good. And this works pretty well, because in that mixed network, while we have a constrained outflow of data, with the inbox, we can receive like these bursts, these peaks of incoming acknowledgement message. That's no problem. And then when A sits there and waits, at some point they say, oh yeah, kind of missing my OK from B. B seems to be offline and unreliable. So what I'm going to do, I pick someone else and just ask them, oh, C, I saw you some time ago. Here's the message again, but this time please act as B. And then C does all the steps. And then if G or F would have more child nodes, they would also continue forwarding them. And then A would check with the timeouts and acknowledgement messages just again, and then be really sure, okay, everyone got their message. And then eventually when B comes offline, they will check their mailbox and say, oh, I got this message. It's pretty old, so you probably don't need to bother forwarding it. So that's something we can do about fault tolerance. But we can also make the entire scheme even more efficient, or at least more fair. Because if you now think A is one of these people who's like do all the work for the group, they do a lot of changes to the document, they're of course sending out a lot of updates, and then it's always B we pick to help us do most of the work. So if we look at our structure, then, well, A sends 3 messages, that's fine, because they're like, it's their choice to do it, but then we always pick on B to do the work. So B needs to do 2 forwards of messages, while the others are a bit slow, so B is kind of a busy bee, so to speak. But that's not really fair, and that puts some burden on a few nodes towards the top of our like tree-like distribution scheme. So how do we actually come up with that tree structure? I haven't talked about that. I just said, oh, kind of the group agrees that we forward things in this certain scheme. So as I said, we assume we have a fixed group, and people have figured out who's part of that group. So all messages will always contain 2 values. So the group ID, so that the individual group members can look up, okay, who are the other members in that group, and the source. Where did this message originate from originally? So they do a lookup, they get the list of members, and then they do a quick resort and just move the source to the top, and then interpret that array as a tree. And by moving the source to the top, we make it also the root node of a tree. And that's how everyone ends up with the same structure, and they know what their actual job is. And then what we can do is we include another integer. So we call that seed value. And then we randomly shuffle our members list when we get that message based on that seed value. So if we pick the same seed value, everyone still arrives at the same structure, but we can just send different seed values, and we can use that to generate vastly different structures, so to make sure that the load is distributed. And we can go even further than that. So because A will send more than one message, and we get the acknowledgement messages, they get an idea, okay, how are the group members behaving? Okay, we might have some stellar performers like DNF, always online, always really quick to reply, and then someone like G is kind of, not sure they're even there anymore. So we want to, for instance, avoid picking G as one of our top-level nodes in our tree, but DNF, they're reliable. Where possible, we pick them. And that's quite easy to do. We just try out, for instance, 100 different seed values, generate their schedules, kind of simulate them against what we learned about the group, and just pick the best seed. And there's a lot of subjectivity in here, like, okay, what's a good result? How long do we keep the data? I leave that for future work if anyone is interested. But that's quite a nice thing that you have this one integer, and you can control a lot about the distribution functionality in that group. And there's another trick we can do. So in the beginning, I said, oh yeah, this multicast inside the system, that doesn't work. Well, kind of. It works when we fix the number. So if we just say we multicast by a factor of 2, then, okay, we have to make all the messages twice the size. That's okay, that's a constant factor. But most importantly, we don't leak information anymore. So the multiplication node will always multiply into 2 messages, so they don't learn anything about our group sizes. And we can even make sure that the messages that come out are all the same size, delayed independently, and maintain all the original properties of our anonymity system. That's actually something I'm not going to go into detail. Have a look at the paper, because for many very subtle reasons, this gets quite verbose in what you need to do. But yeah, it works, but comes at the cost of complexity. So probably a decision one would have to make if you actually want to implement this in practice, or just improve your rate parameters in your mixed network. So at the end, we're always interested, okay, how well are we actually doing? And because those systems already exist in the real world, we said, okay, there's no need for us to also spin up a lot of service on AWS, but instead what we do, we create a deterministic simulator. So we have a Python program, we feed in like configuration, a seed value, let it run, so it runs much faster than if we would do it in real time, and then we get always the same reproducible output, which is really nice for experimentation. It's all open source, so if you ever work in this area, just please fork and work with it. And yeah, this was also part of our Usenix submission. So what does it look like? So here we see the message latency distribution for different group sizes. So x-axis, larger groups, y-axis, latency in seconds. And the whiskers go from P1 to P99, and the boxes are P25, P75. And you can see for large groups, if we just do unicast with normal Loopix parameters, then we are above like 2 minutes. Whereas when we use Rollercoaster and everyone helps distributing, everyone stamps the load together, we're sub 20 seconds, which might be good enough for your use cases. And then the darker green is when we use the P-restricted multicast, whereas the lighter green is if we don't. So it's a small performance boost, but probably not critical. However, if we have the scenario and people are actually going to Greece and sit on the beach and don't help, then we have a problem. So the simple version now performs worse than unicast. So you see the blue is the unicast, and then when people are offline, the green thing shoots up like many hours, because if they're offline for 3 hours, then everyone else in that tree won't get the message. So that looks pretty terrible. But if we then have a fault-tolerant version, then it performs better, and we back at outperforming unicast, which is great. And yeah, that's actually the end of my slide. So it's worked together with Martin Kleppmann, who's now at TU Munich. He was still in Cambridge when we worked on this, and Alistair Beresford, he is my supervisor. And yeah, if you're interested in it, just Google the paper title and it should pop up on a Google Scholar or somewhere. All right, cheers. Thank you.